Hey guys, Mr. Milton here. Today we're going to talk about exponential functions, growth and decay. At the end of this video, you should be able to identify and explain the various parts of an exponential function, and you should be able to write and evaluate an exponential function. Okay? Alright. So, an exponential function's general form. I want you to notice that the variables are x and y. Okay, notice where the x is. It is an exponent. Okay, this is what makes it an exponential function. A is the initial value or starting value. Okay, this value never equals 0. If it equals 0, no matter whether it's growth or decay, it can't. Nothing can grow from 0. Nothing can't lose from 0. Okay, B is the growth or decay factor. Okay, if it's greater than 1, if B is greater than 1, then the function is a growth function. Gets bigger over time. If B is less than 1, then the function is a decay function. Gets smaller over time. Okay, so as we look at these problems here, have y equals 12 times 1.05 to the x. Okay, the initial value is 12. We can tell because this is a number that doesn't have the variable by it. As we look, this is a growth function because b is greater than 1. Okay. Take a second, give you a second to do 2 and 3, answer those problems. So as we looked at here, at number 2, you should see the initial value is 0.4. You should see that it's a growth function because b is greater than 1. And for number 3, its initial value is 5,000. It is a decay function because b is less than 2/3, or less than 1. 2/3 is less than 1. Okay, so pretty quick there of identifying that. So the population of a city is 50,000 and increases by 3% each year. Write an exponential function to represent this situation, and then tell how many people live in the city after 5 years. So, looking at the situation, we should be able to identify first the initial value. It says the population of a city is 50,000, so from where we started, or where we were able to see it, it's 50,000. That's where it starts. It says that the population increases by 3% each year. So, is this going to be growth or decay? Well, it's growth, because it says it increases. Now, we'll come back to B in just a second. Okay, once you find the functions of, or once you find the values of A and B, you can write the function. The A value is typically given, but the B value takes a little work. So, growth rate in this case is 3%. If you use 0.03 as your B value, okay, I'm showing my calculator here. If we plug in our values and we said, okay, A is 50,000, and we said 0.03. So after 1 year, since it had the 0.03 growth rate, or 3% growth rate, how many people should we have? Well, it says after 1 year, we'd have 1,500 people. Does this make sense? No, the answer is no, it can't make sense, because if it's a growth rate, why are we losing so many people? We lost like 49,000 people in a year when we said it's growing. Okay, so to find the B value, you either take the percentage R and you either add it or subtract it from 1. So if it's growth, you do 1 plus the rate, and if it's decay, you do 1 minus the rate. And so you can think of it as how much percentage of things do I get to keep for the next year, or for the next cycle, whatever you want to say the time limit is. So here it says we get 3% each year. We get to add to that 3%. So we have 100%, and we add to the 3%, so we'd write it as 1.03 in this case, because it's 1 plus 0.03. Okay, and so now we get to see, okay, would it make more sense as 1.03? The answer is yes, because after 1 year, say we had 51,500 people. And so, yeah, that makes sense if we're growing 3%, that we'd have about 1,000 people more, almost 2,000 people more. Okay, so in the previous example, A was 5,000, or 50,000, sorry, and B was 1.03. So the exponential function is y equals our initial value, 50,000, plus our growth rate to the x. So the population in 5 years, 50,000 times 1.03 to the 5th, would be 57,963 people. Okay, now when we look at this decimal, we have to say, it's a situation where we have to say, does it make sense to use a decimal? I know that a lot of you guys like hard and fast rules, but we have to say, does it make sense? Now, if we were talking about money or the value of a car, in this problem, we'd say, okay, yeah, we'd do 57,963.70 because it makes sense with money. But if we're talking about people, I hope that after 5 years we don't have 0.7 of a person running around or laying around. I don't know how 0.7 of a person moves. Okay, so we would not use that decimal. Okay, let's look at the next problem. It says a new car costing $20,000 depreciates in value 16% each year. Write an exponential function to represent the situation, and then find the value of the car after 7 years. So here we go. We know that this function should look something like y equals a times b to the x. So y we'll keep there. A is our initial value, 20,000. That's what it started off as. B is where we have to think a little bit. It says it depreciates, so is this going to be growth or decay? Well, depreciates means that it gets less. So it's a decay function. And it gets less by 16%. So again, think of it as how much of this do I get to keep? Well, you lose 16%. So you do 1 minus 0.16. You get to keep 84%. That's the B value, 0.84 to the x. Okay, and so now as we look at it, we can do this problem, 20,000 times 0.84 to the 7th power. And then it says that after 7 years, the car is worth $5,901.80. It says after 15 years, the buyer decides to sell the car for $3,000. Is it a fair price? So we can use the same function and now change our exponent from 7 to 15. And it says that after 15 years, so 20,000, 0.84 to the 15 equals $1,462.90, let's say 2 cents to make this buyer a little bit more reasonable. So he's trying to sell this car for double its worth. Is this a fair price? No, comma. It's half of the sell. It's worth half the selling price. So if this guy kept it in mint condition, he might want to lower the price. Okay. Because he's trying to sell it for a lot more than it's worth. Alright. In the movie Pay It Forward, an idea is brought about by a boy who wants to make a difference in the world. The concept he comes up with is to do one unexpected nice thing for 3 people. And then each of those 3 people to pay it forward by doing something nice for 3 more people, and so on. So write an exponential function to represent this situation. So here's our function. How many people started? Well, one person, one boy, thought of this cool idea. He wanted to do something nice for 3 people. So, what's our, this is obviously a growth function. What's our growth rate, or growth factor? Well, you're trying to think of the percentage that it's growing by. So he started off with 1, he's going to do it for 3 people. So from 1 to 3, how much does that grow? That's 300%. So we can say 3 times, okay? Or if it says double or quadruple, we can look at it as that too and just think of those, okay? Because double just means 200%. Okay, or triple means 300%. And he wants each of those people to continue that same rate, that one person does something nice for 3 people. Okay, and he wants to pay it forward, and so on and so on and so on. So depending on how many rounds of paying it forward, that's the function. If this happens 5 times, how many people are affected? So here we have our function. I want you guys to bring in these answers to class. Complete it. Alright, see it. Growth and decay rate there.